accept Bitcoin from someone, unless you go maybe consult some centralized blacklist server. And if you're trusting a centralized blacklist server, why have Bitcoin in the first place? So it's important that we build into the system, wherever we can, good tools to preserve fungibility. And this can be traded off against other considerations, right? Like, one of the powerful things you can do with Bitcoin is build transparency that's provable in a way that you couldn't have before. But that's not incompatible with privacy. You can layer transparency, you can layer accountability on top of a private system, but turning it around and trying to build privacy on a system that doesn't have it is much harder. This goes a little bit beyond just the sort of practical day-to-day security against your neighbors. There's a significant civil rights issue related to the privacy of money. Because as much as people decry the negative outcomes in rulings like Citizens United, to effectively speak your mind, to effectively seek political power, you need to be able to spend money. And if powerful forces can stop you from spending money, your voice is suppressed. And this is not a radical political view, right? This is a normal, like, you know, Supreme Court justices from both sides of the political spectrum there hold view that money is important to our ability to speak. So, why privacy in Bitcoin Core? I personally view Bitcoin Core as a best practices implementation. We're not necessarily trying to be the most whiz-bangy, but we're taking a serious approach to building software that's very high quality and trying to implement the best techniques that we can implement. Another aspect here is that Bitcoin Core is a full node. And what a full node is a system that autonomously validates all the information in the Bitcoin network without trusting anyone. And this has significant implications for privacy. So one of the things that's occurred that sort of surprised me in Bitcoin Core is I've actually been asked by companies and by researchers to not fix privacy bugs in Bitcoin Core. I mean, literally, like, here's a bug, tell me about it, but please don't fix it. And I think this is really short-sighted for all the reasons I just said. But beyond that, in Bitcoin Core, we would not intentionally add a privacy-harming misfeature to the system. And I think not fixing a bug is equivalent, or even worse. Because if we intentionally add a privacy-harming feature, at least, you know, you can see it and you can turn it off. But a missing fix is invisible. So I think the software should serve only one interest, and that's the interest of its users. So there's been some recent public drama about surveillance attacks and things in the Bitcoin network. This has actually been going on for a very long time. The passive surveillance in the Bitcoin networks existed since at least the beginning of 2011, where people run nodes that basically serve to de-anonymize users by trying to trace transactions through the network. More recently, people have been spinning up these farms of Sybil nodes that pretend to be other nodes in the network to try to gather more traffic to them so they can analyze it better. So Bitcoin Core has basic protections. It won't connect multiple times to the same net group, so you need to get lots of net groups to attack the network. But those protections are only basic. And one interesting point here is that any weakness in this domain encourages wasting network resources. So people will spin up nodes and they try to connect to everybody, and they're wasting capacity for the whole network because the system wasn't private. If we make the system more private, there's no incentive to spin up a bunch of systems that go and connect to everyone and waste a bunch of capacity. So long-standing advice is to run Bitcoin Core over Tor. And Tor is great. It's not perfect. It's particularly weak against state attackers. It's vulnerable to denial of service. But it's usually strictly better than not using Tor. There's been some discussion around some of these Sybil attacks and things, people saying that they're unlawful because they violate the Computer Fraud and Abuse Act in the US, or that they violate various EU privacy directives. And that may be true. I have no opinion on that. But in the space of Bitcoin, we already have to defend against attackers who don't care about their public image, and they don't care about what the law says. And so since we have to do that, our most powerful tool to use that is technology. So if people want to pursue other avenues to making people behave, that's fine. But my focus is on, you know, how can we improve the technology? So one of the areas that we've been improving recently is with respect to Eclipse attacks. This is where people try to get your node to only connect to them, or to mostly connect to them, by Sybil attacking and flooding you with address advertisements. So Bitcoin Core keeps a table of peers it knows about, and has a very sophisticated cryptographic scheme that makes it difficult for someone to gain extra space in that table. But there have been some recent simulation results that found that it wasn't quite as good as we expected. There were some places where randomization in the algorithm actually allowed an attacker to get a greater concentration. So there's a paper recently published on this, and prior to the publication of the paper, the authors worked with us, and we went and implemented a half dozen different fixes. So we expanded the tables, didn't promiscuously take extra advertisements, and so on. And these fixes will all be in 0.10.1, which should be available in a couple of days. In general, people trying to connect to a lot of the network has been sort of a long-term problem. And so there have been a number of things discussed and sort of in the works on having tools to sort of dissuade that activity. So one of them is having a proof of work system where you can get prioritized connections to the network by doing some proof of work. So it's more expensive to use up capacity on the network. I proposed a storage hard proof of work scheme like maybe a year ago. Sergio has another number theoretic scheme. And they're all kind of complicated and don't completely solve the problem. And so it's a little difficult prioritizing them. If it clearly solved the problem, we'd deploy it right away. And if it was really simple but didn't, we'd probably deploy it right away. But the combination's a little messy. And so this is still kind of in a researchy phase. I've been working on a tool that can run alongside Bitcoin Core where you have peers that you trust, your friends, whatever, and they can compare notes without telling each other who they're connected to, but they'll learn who they are connected to in common. So you can identify people who are connecting to too much of the network and automatically ban them. And some people are doing this today manually, just like, oh, who are you connected to? Hey, they're connected to me too, let's ban them. So there's a number of other network level improvements that impact privacy. There's an issue in Bitcoin Core today where your connections out via Tor will end up on the same circuit sometimes as your web browser connections via Tor, which can leak some information about your identity. There's an information leak where someone can send address messages to you with certain timestamps or view the timestamps on address messages you send, and from that learn more about the network topology. And this allows them to target partitioning attacks on the network. And it also weakens your privacy because they can tell what graph path the transaction flowed through in the network. We've also been working on things to improve the batching of relaying of transactions to provide a bit more privacy. One of the features that's gone into the 0.11 branch right now is this wallet relay improvement. So right now with Bitcoin Core, receiving transactions, you're completely private. There's nothing you send that identifies that you've received a transaction. But when you send the transaction, and someone can use that to sort of identify what you're doing, what your transactions are. And if your transaction doesn't immediately make it into the blockchain, you will rebroadcast it periodically. And we believe that some people have actually used this to try to trace users in the network. So there's a new flag in the 0.11 branch that lets you turn off wallet relaying, and it becomes manual, so you can manually send it. Now, manually sending your transactions by itself isn't all that useful. But what it means is that somebody can create a little program that runs alongside Bitcoin Core, and when you make a transaction, it'll pull it out and then send it to the network some other way. So it could use a high latency mix network like Mixmaster or BitMessage. And the cool thing about it is it can be separate, so you don't have to learn all about developing in Bitcoin Core. You don't have to seek my permission. You can just go write it in whatever language you want, run it alongside Bitcoin Core. If it's useful and people use it, it's something we might pull in as a contrib in Bitcoin Core. So it's a nice way to sort of scale up there. Another area that we're working on in privacy is not actually privacy, but it has big implications. So we've been working a lot on making it easier for users to run full nodes. So as I mentioned before, full nodes have fundamental privacy advantages. The existing models for SPV, the direct Bitcoin J style SPV and Electrum, are fundamentally weak from a privacy perspective. Bitcoin J sends these Bloom filters, and in practice, the Bloom filters uniquely identify the wallet. The parameters can be tweaked to make it a little more private, but it's still fundamentally weak, and you don't know how strong it is. So you might think you're private and then find out you're not. Similar for Electrum, Electrum sends the server a list of addresses, and anyone can run an Electrum server. The nodes by default connect promiscuously to an IRC network to find Electrum servers, so you can easily spy on the Electrum network. And I don't say this to fault those approaches. It's necessary that we have light nodes. It's the only way you're reasonably going to run Bitcoin on a cell phone. But it's not as private. And so if we can make it so that more people can run full nodes, more people can enjoy more privacy, we get more fungibility in Bitcoin, the world is better for it. But right now, to run a Bitcoin full node, you need 30 plus gigabytes of disk space. And there's some behaviors in Bitcoin Core with respect to bandwidth burstiness that play poorly with the buffering on common consumer routers. So if you send a bunch of data all at once, many consumer routers have too much buffering. This is called buffer bloat, and you'll see like 1 second ping times. And then you get irritated and like turn off Bitcoin on your network. So in 0.11, we have is pruning in play, and pruning allows you to run a full node that's still autonomously validating the network. It's still fully private, but it doesn't store the complete blockchain history. And so you can run a node with more like a gigabyte of space. And we're planning on implementing some automatic bandwidth rate limiting. And the main question I'm trying to solve with that is there a way I can make it self-tuning so the user doesn't have to go and set settings and we can still avoid causing long delays. And I'm not sure if I'm going to be able to do that. There are still many things that we'd like to do for privacy and that I'd like to see for privacy in Bitcoin Core that we haven't really started on yet. So things like the wallet in it, the coin selection algorithm is fundamentally bad for privacy because it's incompatible with address reuse. If you reuse addresses at all with the Bitcoin Core wallet, it will rapidly link together the addresses and then totally blow up your privacy. And this is technically easy to fix. A wallet just needs to try to spend from addresses in groups and should try to avoid interlinking them. And we actually have code in the code base that traces what addresses are interlinked with what addresses. But we don't have enough testing for the wallet infrastructure right now, and so it's hard for anyone to go and develop in it and be confident that they're not breaking the wallet code. There's been a ton of development in the coin join space, and this is a sort of casual privacy improving transaction style that I described a year and a half ago or whatever. And there's no implementation of CoinJoin for or in Bitcoin Core yet, but there are many out on the network, and there's some research results showing that there's a significant number of CoinJoin transactions happening, which I'm happy to see. So the sort of design for good CoinJoin systems is still being fleshed out by people, but as that matures, I'd like to see an implementation of that in Bitcoin Core. There's also this thing that's called stealth addresses, and I really hate the name because it's intentionally edgy, and it's really doing something that's quite pedestrian. That's been promoted by the dark wallet folks. And I like to call it reusable addresses, and it's a thing that we've been talking about for years. We're calling them ECDH addresses previously. But the notion of these stealth addresses is that you give someone an address, and every time they reuse the address, there's sort of a randomly generated different address that appears in the blockchain, and so those transactions aren't linked together. But there's an existing proposal for this, but it's basically unmaintained, and it gets a bunch of things wrong. The basic design right now makes the SPV privacy problem even worse. So it's very difficult to deploy a new address style on the Bitcoin network. I mean, we created P2SH back in the beginning of 2012, and it took years before all wallets could support it. And so we want to act very intentionally with this to make sure that we implement a right spec and don't have people gyrating on different approaches here. All right, so that's some of the things that's going along with privacy in Bitcoin Core. So now I'm going to switch gears for a minute and talk a little more forward-facing. So when we deploy new technology for the Bitcoin network, we have to think sort of far into the future for two reasons. One, it takes a lot of work to deploy a new tool into a big distributed network, particularly a consensus network, but also because we need to make sure that our pipeline of changes don't sort of interfere with future changes. So I've been giving a lot of thought with a number of other people on what kinds of cool things can we do to make multi-signature more powerful in the future. And we've come up with these criteria that we think that are good to have in multi-signature schemes. So multi-signature, I think everyone here is familiar with it, but it's really solving this sort of fundamental problem that in Bitcoin, there is no other recourse than the network. That if somebody steals your coins are stolen. You can't go get a clawback. And also, computer security is a joke. There's no trustworthy devices. Everything has malware. Everything's remotely controllable by someone. And so the idea with multisig is, hey, well, maybe if we take multiple devices, that they won't all be compromised at once, and we can get some actual security. And so you can define an access policy. These coins can be spent if A and B agree. Or these coins can be spent if 2 of 3 of these parties agree, or so on. But, and we've had, multisig has been in Bitcoin since the very first day, and we added some features to make it more accessible with P2SH, and that took years to get deployed. So it's important to think about this to sort of get the pipeline going. One of the problems with multisig today is that it's costly. If you use 2 of 3 today, it increases your transaction sizes by a factor of 2.5, roughly. And that means 2.5 transaction fees. It also means a reduction in the total network scalability. And that also has a direct impact on the decentralization of the network, because the more expensive it is to run nodes in the system, the less people that will run them, and the more centralized the system becomes. So we want to have a good handling of this. And that's only for 2 of 3. The bigger your multisig, the more the cost is. And so there's a tension where your security says use some big multisig policy, but practicality says, no, you're not going to do that. And so it would be nice to improve that. And we can improve it. So I want to talk a little bit about some crypto system background stuff to sort of let you understand how we can improve this. So there's an alternative to ECDSA called Schnorr. And Schnorr is older than ECDSA, and it's simpler and more straightforward, and it has robust security proofs, and it's a little bit faster as well. But Schnorr was patented, and as we've seen in the history of cryptography, patenting is poison. Any patented crypto system sees virtually no deployment at all. People would rather be insecure than deploy a patented crypto system. And of course, patenting is actively incompatible with decentralization because the patent holder owns the technology. So in any case, the NSA came up with this nice workaround to the Schnorr patent. And ECDSA is very similar to it, but not algebraically equivalent. And the world has deployed ECDSA, but Schnorr still exists, has lots of academic research on it. But one of the cool things about Schnorr is that it can do multi-signature in a very straightforward and scalable way. It's sort of like Schnorr multi-signature works the way an idiot would tell you it worked if they knew nothing about cryptography. So the way it works is that if you want to have a 2 of 2 signature with 2 parties, you add together 2 pub key, and to get the 2 of 2 signature, you add together their signatures. And that is a 2 of 2 signature in Schnorr. Now there's some details to actually go and implement it, but that's the basic idea of it. And it just works. It gives you a 2 of 2 signature. So not only does it give you a 2 of 2 signature, but the scheme can actually be extended to support an arbitrary threshold, actually an arbitrary cascade of thresholds, an arbitrary monotone Boolean function, which is really cool. So you can get any policy you want, and the signature looks like a 1 of 1. You can't distinguish it from a 1 of 1. It's the size of a 1 of 1. It scales like a 1 of 1. That's awesome. Efficiency solved. But when we went to implement this, so Peter and Andrew Polstra went and started implementing. Peter implemented an ECDSA or a Schnorr verifier, and Andrew went and started making the key sharing tools to do thresholds. And what we realized is, hey, wait a minute. In order to make a threshold Schnorr key, the signers have to collaborate to generate the pub keys. So you can't just take some pub keys you found on the network or someone put in a directory and derive the threshold key. The signers have to interact. And if the threshold is big, they actually have to interact a whole lot. And that's a little problematic to deploy. We've seen in the Bitcoin ecosystem, there are really cool things you can do with script, but if it needs a complex state machine in the client, people don't build the software to use them. So that's sort of fundamentally worse than what we have today, even though it's so much more efficient. It's worse in that way. So what other criteria, what other things can we think about should a signature system be meeting? So one of them is accountability, or so I call it. And this is that in the Bitcoin multi-sig system today, you can tell who signed. If you have a 2 of 3, you can tell which 2 of 3 signed your transaction. And this is actually quite important, because if one of these 2 of 3 is, say, your attorney, and they sign a transaction you didn't authorize, you want to know. Not only do you want to know, you want to be able to prove to the world they did it, because you might want to sue them, you might want to discredit them, you want to communicate about this. And so this is a useful property for a multi-signature scheme to have. And this Schnorr multi-signature, because it looks just like a 1 of 1, doesn't have it. You can't tell which of the 2 of 3 signed or any other version of the threshold. So this is a criteria that would be useful to have. Another one is one I hinted to before, and I call it usability. And basically, many of the multi-signature schemes require round trips between the participants. In the Bitcoin multi-sig scheme today, someone can propose a transaction, sign it, send it to the next person, they sign it, all the way to the end, put it to the blockchain, and they're done. No round trips, just one way through. So with a N of N Schnorr, you can do basically that. You need one round trip to establish the nonce, which you can do in advance. And that's fine. But you have to have lots and lots of round trips to establish the threshold, and that's not fine. And there are some other more efficient multi-sig schemes that require many rounds during signing. So you can imagine you have some hardware wallets distributed in safes, and you want to sign a transaction, and you have to go to and from the safe over and over again to complete your transaction. No one's going to use that. And building the software to support that and teaching people how to use that, it would be a real barrier. And so usability is one of the extra constraints that we need to worry about. Another one is privacy. So I talked before about why privacy is important. In the context of multi-signature, privacy is useful because if an attacker knows your policy, he knows what to target. Oh, you're 2 of 3. I kidnap these 2 people. I get the keys. I got the money. If he doesn't know what your policy is, well, maybe it's 8 people he has to go and kidnap, and that's a different trade-off. There's also this identifying issue where if you're using an odd policy, you're the only 6 of 8 on the blockchain, then people can trace your transactions with the commercial implications I mentioned before. So when talking about privacy, it sounds kind of like privacy is incompatible with accountability, but it's not true. Accountability means that the participants and the people they designate need to know what's going on in the transaction. And privacy is a statement about third parties. So this direct Schnorr multi-signature stuff, it's got great privacy. No one can tell what the policy is except the participants. But it loses accountability. And Bitcoin today has great accountability, but it has very poor privacy. So there are some papers recently about threshold ECDSA. And this is some fancy cryptographic techniques to do the same stuff as the Schnorr multi-signature, but use it on the existing infrastructure deployed in the network today. So these schemes have limitations. In particular, they fail on usability, and they're also like Schnorr multi-signature, so they have no accountability. But it works today, in theory. There's no implementations right now that don't require a trusted dealer. But these may be interesting for applications where you don't care about the limitations, at least once someone gets around to implementing them without the trusted dealer. Now I have to say that the first version of the paper of this said you could do it with the trusted dealer or without a trusted dealer. I argued with the authors. They eventually convinced me that yes, you could really do it. And then they had retracted their paper and said, no, you really need a trusted dealer to generate the keys. They've since gone back and come up with a scheme that I believe, without their convincing, will work without a trusted dealer, but no one's implemented it yet. Now, I'm not going to talk any further about this. It may be interesting, but I think it's not sort of the longer term, more interesting area. So I want to talk about a couple of schemes that I've been working on and come up with that get a different mix of these criteria. One I call TREECHECKSIG. And we start with the observation that a N of N, an all-signed Schnorr signature, meets the criteria in terms of it's efficient, and it doesn't require a bunch of round trips, and it's actually completely accountable. Because if all signed, well, all signed. So N of N is good for accountability. So what we can do is you can imagine a larger threshold, like a 2 of 3 signature. Well, a 2 of 3 signature, a 2 of 3 policy, could be satisfied by any of 3 2 of 2s. And so you can enumerate all of the possible satisfactions for a threshold, and there are m choose n of them, and you can build a hash tree over them, like we use for SPP proofs in Bitcoin. And then in your signature, you can prove to the network, this pub key is from this set of permitted pub keys, and you provide just the N of N signature. Now this is interesting because it scales fairly well. It has improved efficiency over the current world, although it's not as efficient as a 1 of 1. But it's completely accountable. The parties know who signed. But if you randomize the order of the N of N keys in it, the only thing someone can learn from looking at it is an upper bound on the size of the threshold you're using. And it's relatively cheap to make the size a little bit artificially larger, so you can add 1 hash, double the size. So privacy is pretty good too. The verification efficiency is great. It's basically constant time to verify. It's the same as checking 1 signature plus some hash operations. But the real problem with this scheme is that if you want to talk about doing a big threshold, and by big I mean more than say 20 participants, the tree becomes so large that you can't compute it to compute the pub key. Now the network doesn't have to do this, the participants do, but it becomes impractical fast because of this binomial blowup. So MULTICHECKSIG was a idea to try to fix this, which is to say instead of building this big hash tree where you have to pre-compute all of the satisfying combinations, why not have the signer show the network all of the M pub keys that are participating, and then have the verifier compute the N of N. So I can take the pub keys, the verifier in the network, have a list of them, and I say, okay, this set is signing, and the verifier can add up the pub keys to compute the N of N pub key, and then you can provide a signature with that. So this is good accountability, but it's not private because the network can now see exactly which combination is signing. And it works with 1 pass round, so it's usable. The size isn't great. It's always larger than the tree version, even though the tree version has that binomial blowup in it. But the verification is fast. So that's a neat set of trade-offs. And then taking from this idea, I thought, well, can we do better? And so I came up with this notion that I call polychecksig. And the idea is to take this multichecksig and say, instead of revealing the pub keys of the participants in the signature, can we reveal some linear formula on the pub keys in our signature, and then ask the verifier to do some linear formula on our pub keys to compute the key that you verify. So I've shown how this works concretely. Say we want to do a 3 of 4. So 3 people, 1 is not signing. That means we need to compute a n of n pub key that we're going to sign with that has left out 1 participant. And so we make our 2 pub keys that we reveal to the network be the sum of the participants. Participant A, B, C, D. That's the first value we tell the network. And then we tell the network another public value, which is the sum of participant A plus 2 times the participant B's key, plus 3 times the participant C's key, plus 4 times the participant D's key. Now, if you know how to sign with key A, then you can sign with 8 times A or any other constant, because it's just multiplying your private key. Then we can ask the network, we can say to the network, hey, we want to do this signature and we don't want C to participate. And when we do that, the network can compute a new pub key V. And it computes that pub key as 3 times the 0.1 minus 0.2. And if you write this out, what that value is the same as 2 times A plus B minus D. There's no C term. C canceled out. This scheme can be extended by adding additional quadratic, cubic, and quartic terms to it by having more public points, and you can cancel out an arbitrary number of values. So you can say, I want to have some threshold, and say, 3 points are not going to sign in it. You need to express 4 values to the network. So the scaling is m minus n plus 1. You can then take these values that you're sending to the network, the P1, P2, Pn, whatever, and encode them in an unbalanced cache tree, so you only have to reveal to the network as many as you're going to cancel, just the first n of them. And what that means is that you might have a 50 of 100 signature, but if all 100 participants are available, you compute that as a 100 of 100. You reveal only the first term of the polynomial, and then you provide that 100 of 100 signature. Your transaction looks like a 1 of 1. And so you get perfect efficiency in the case where all of your signers were available. And perfect privacy in that case, because you revealed nothing about your actual policy. If you need to reveal more people because some signers were offline, you can do that, and you leak a little bit about your policy at that point. So I mentioned in the list of features Composable, and I haven't talked about it yet. So Composable is this notion that it should be possible for you to have your own policy, and neither of you should care about what each other's policy is, and I should be able to create a policy of your policies. So you can use 2 of 3, and you can use 2 of 3, and I can make a 2 of 2 of you. And I shouldn't have to care, and you should both be able to sign. Now, these schemes themselves don't do anything for composability directly, but we can overlay a higher level scheme that achieves composability. And what we found while exploring this is that if the higher level scheme is only able to express a monotone Boolean function, that is to say, signatures where someone extra signing will never make your signature untrue, then it's quite easy to write software that can handle unknown parts. You can write a software where it says, OK, I'll sign the parts I know, and I'll not worry about the rest. And so we think that'll make us, if we overlay a scheme that does this on top, then we can get something that's much more composable, although we've not sort of explored the whole space of this yet. So I have a sort of comparison chart here, and if you notice, my slides are all very wordy, so you can reference it later. But just to give you an idea of how the different schemes scale. So 2 of 3 signature, just having one input in a transaction is like a 250-byte signature. And all schemes are relatively in the ballpark for that. But if you start talking about doing things like, a 13 of 15, you end up with 1472 bytes in the Bitcoin transaction. And the other schemes we have are much smaller. And if you try to do something like a 990 of 1,000, you can't even put a single one of those in a standard Bitcoin transaction. It's over 100K. And forbid you need to put in more than one signature in the transaction. But all of these are achievable with relatively good efficiency. And as we see for this polysig scheme here, I have ranges for the sizes, because if all participate, you can get a very small signature. And so even though you have a 990 of 1,000, if all 1,000 people are online, your signature size is 142 bytes. It's great. So that's been some stuff that we've been working on in the space. And it's not clear how this will develop. Some of these ideas are very complementary and can be merged. It's just sort of exploring the space, but expect to see some more development on making these concrete in the future. I am doing okay on time, good. So I want to talk now about a thing that I'm calling the art of selection cryptography. And although I'm using the word cryptography here, this is really the more philosophical section of my talk. So before I can tell you what selection cryptography is, I actually feel that I need to attempt a redefinition of cryptography. Because the definition that people use for cryptography in the world today is broken. It's actually wrong. It doesn't match what people use. You go to Wikipedia or any dictionary, they will say that the cryptography is secret writing or enciphering and deciphering messages in code. And that definition doesn't have anything to do with many of the things that we call cryptography today. It doesn't speak to digital signatures. It doesn't speak to compact or zero-knowledge proofs. It doesn't speak to the technique of private information retrieval, which is what allows you to query a database without anyone learning what you queried in it. Hash functions. It doesn't talk to things like the cipher suite negotiation in TLS, which has constantly been a source of security vulnerabilities. Right? You look at TLS and say that TLS is cryptography. It's a cryptographic protocol. But you look in the dictionary says that only the AES part is cryptography. And that's just ridiculous. Bitcoin itself. You can build a Bitcoin node today that has absolutely no cryptography in it. The only thing we use cryptography for, or the cryptography by the dictionary definition, is wallet encryption. And then you never send the messages to anyone else. So to explain my explanation, I want to take a step back and sort of give a little bit of my view on the world. So back in the early 90s, as I was sort of politically coming of age and on the internet, I was very excited and involved with Cycrypt News Group and all of the activity around the prosecution of hackers and the export of cryptographic software and this grand sort of political vision that the internet and networks would change everything. And there was this rallying cry, right? Information wants to be free. And I knew in my bones that this was really true. And that we were going to use computers, which turn everything into information, and we're going to use networks to hook all the people together, and we're going to change the world. We're going to change the power balances, make people more equal, and everyone would have access to all the world's knowledge, and they would all fulfill their potential. But that's a very political take on something, which, in fact, I actually think is better described as a law of nature. It isn't just that I want information to be free. No, information really wants to be free. It is fundamental that information will percolate out into every little nook and cranny, and you can't control it. And the result is that often bad things happen because information wants to be free. Right? Sunlight is the ultimate solvent, but solvents corrode as well as clean. And so my email wants to be read by the NSA. Right? When I try to log into my server, it can't tell me from you because you can just replay my login, and now you're logged in as me. When you go and browse the internet, people learn about what's interesting to you. They sort of see inside your mind what used to be completely private and had no danger of being learned by others. When I go to research something, marketers can send out spam cheaply, and that spam is just as visible as the information I seek. All right. If I want to build a digital cache system, I can't, because digital information can be perfectly copied, and all the copies are just as good as all the others. And so a money that you can just copy isn't much of a money. And so we have an environment where there are powerful parties that have more ability to use this fundamental nature of information, and this goal of everyone being more equal and everyone being more empowered may not come true. And so I would like to propose this definition of cryptography that says that cryptography is that art and science with which we try to fight this fundamental nature of information, that we try to bend it to our political will and to serve our moral purposes, and to direct it to human ends against all chance and all eventuality and all efforts to oppose it. So this is a very sort of broad definition. And it actually encompasses, I think, everything that we properly should call cryptography, and a number of things that we haven't normally called cryptography, like computer security, or even sometimes the drafting of legislation. And I don't really offer this lightly. I've thought about this for a long time, and I think this definition leads to pretty good intuitions about the kinds of things that have cryptographic considerations. So often we get, as technologists, very excited about, I have this cryptographic tool to solve this problem. You want to read my email? Bam, encryption. You want to track my stuff? Bam, private information retrieval. Bam, digital signatures. I'm going to solve all the problems with some cryptographic tool. And that's very exciting, to say that you can sort of fight back against things you don't like in the world with a bunch of math. So that's really cool. But sometimes we get really caught up in the coolness of that, and we forget that we're really fighting the fundamental nature of information, and it's hard. In fact, it's so hard that it might not be possible to make secure crypto systems. Every practical crypto system in the world is predicated on a set of strong assumptions, that we assume some mathematical problem is intractable. Do we know it's intractable? We don't know how to break it yet. And over time, we've seen many crypto systems have actually been broken as those assumptions have fallen. Few people believe it to be the case, but it may actually be fundamentally impossible to build strong cryptography. And this is also why that if you were able to build a provably secure asymmetric crypto system that had no strong assumptions in it, this would directly be a proof that P does not equal NP, which is a problem people have been studying since the 70s, and that you can win $1 million prize for proving. Oh, and by the way, you can still prove P does not equal NP without being able to build a secure crypto system. So building a secure crypto system is actually harder than proving that P does not equal NP. So don't expect people to solve this anytime soon. A really important point here is that attacks on crypto systems are themselves information that wants to be free. And this gives attackers a tremendous advantage. And we often underestimate how powerful computers have become because our software is sort of bloated and slow and has many layers. You can imagine that a computer is sort of the intellectual equivalent of someone who is doing arithmetic for you, but 1 billion times faster. And so if you can attack a crypto system by applying a lot of force, computers are a force multiplier. And so everyone who is attacking your crypto systems, if they have a desktop computer, it's like them having an army of 1 billion imbeciles. Then they might be imbeciles, but 1 billion of them. And that's before they get a botnet. And then they have 100,000 times that, or an NSA data center. And so if someone's able to attack your crypto system and reduce it to a state where it's still a huge haystack that they're searching for a needle in, they can then apply a lot of computing power to go further. And we can even use the computing power to search for complicated algebraic solutions to the systems as well. So it's not just the number crunching. It actually expands our intellectual capacity to attack the systems. And this more strongly favors attackers than it does defenders in general. And in order to build a secure cryptographic system, we have to secure it against any eventuality. And so as a result, virtually everything people propose ends up being broken. And this is certainly true for everything that I've touched. Some things aren't, but you think of something and you try it out and go, oh, wait, no, you can break it. There's a whole subfield in academia about provable cryptography, and people, I think, get confused about what provable cryptography means. Provable cryptography is about cryptography that is secure, if the proof is right, so long as the assumptions hold. Now, this is a little surprising, because you would say, well, why wouldn't it be secure if the assumptions hold? Turns out that's actually hard to achieve, too. And many things that occur in provable cryptography, there's this pressure to publish in cryptographic research papers. You have to include proofs. And the easiest way to get a proof of your cryptography is to just adopt a stronger assumption. And so there's actually a lot of provable cryptography that's broken because they adopted assumptions that were wrong. They sounded plausible. They turned out to not be true, or because their proofs were weak, or they proved some vacuous property that didn't map to security in a practical sense. So I don't mean to sort of say that cryptography is the only thing that people do that's hard, right? Civil engineering is a tremendously difficult discipline, and lives are on the line if a building doesn't stand up. But usually in the case of civil engineering, you're worried about a more limited set of natural causes, and you're not generally worried about the billion army of imbeciles and all the world's efforts to nearly costlessly attack you. If you ask somebody to build a building that cannot be taken down through all the force in the world, they tell you that you were nuts. They'd probably ask for $1 trillion first and then tell you that you were nuts, but still take the $1 trillion. We're only able to really think about doing cryptography at all because we can use software, and software is a really great building block for things. It's incredibly flexible, and we have tremendous tools to write software that is more complicated than anything else. Like a very complicated piece of mechanical engineering, something like the space shuttle, on the fringe of what we can do as a civilization, is of something with on the order of 200,000 parts. But if you look at a conventional piece of software that you use every day, say Firefox, that's 17 million lines of code. And almost any one of those lines of code could be undermining your security. Typical figures for defect rates for software in industry are numbers like 15 to 50 bugs per 1,000 lines of code. The numbers vary a lot. So maybe for software where people care, maybe it's more like 1. But 1 per 1,000, and we're talking about programs that are 17 million. A complete GNU Linux desktop is like 600 million lines of code. So software, despite our awesome tools to build it, is very buggy. Making it cryptographically secure is even harder. So there's this quote that I've seen that I love, right? That the software testing is making sure your program does what it's supposed to do. And security testing is making sure that that's all that it does. And that is fundamentally harder. So yeah, right, like I've hopefully impressed that this is sort of a hard area. And this isn't news to me. So there's this adage on the internet that's gone around for a long time, which is basically say, never write your own cryptography, because people did appreciate that it's hard and everyone gets it wrong. But I think that's actually bad advice. I call that the abstinence-only approach to cryptographic education. And one of the results is kind of like the provable security stuff. If you tell people never write your own cryptography, we'll just redefine cryptography to be some narrow part. Like, oh, I didn't re-implement AES. Right? No one, like, all right, some people have re-implemented AES and had timing attack problems with it. But really, very few systems are broken by people re-implementing underlying cryptographic primitives, although there's plenty of potential to do so. Systems are more often broken by their higher level violation of the assumptions in them. And even if you follow this never write your own cryptography, now you've got this other problem, which is now you have to go and select the cryptography that you use, and you have to use it in a way that doesn't break that software's assumptions. So I like to just re-emphasize that if people are counting on a program to sort of fight this fundamental nature of information, the program as a whole is cryptographic. That doesn't mean that you can't write it, that you shouldn't write it, but it means you need to sort of step up to the plate and recognize the risks. What does come along with some bad news, though, right? I can't tell you how to write a secure cryptographic program. Said before, we don't even know that it's possible. We do know that some things are unsafe. You shouldn't do this, you should do that. But usually that advice is very application specific. It's not general advice. And so in general, what I can say is that we should face it frankly, we should communicate and learn from our mistakes and advance the art. So in the interest of advancing the art, I wanted to sort of talk a little bit about a special kind of cryptography that is probably the most common cryptography in the world. And I call it selection cryptography. It is the crypto system of picking crypto systems, right? And you should think about when you select a cryptographic tool or build software that has cryptographic implications, what selections are you making, and are those good from an adversarial cryptographic perspective? So I see a lot of norm in the Bitcoin space is to build tools out of primitives that were found on GitHub. And I don't say that to deride it. There's some fantastic code on GitHub, including my own. But not all code on GitHub is good. And so we can think about, like, how can we go about doing a better job at selection? If you're a domain expert in the particular cryptographic tools that you're using, then you can review it as a true reviewer. That's great, and I hope that everyone who can does. But if you're selecting someone else's code, you probably can't review it. You don't understand the underlying parts, and you shouldn't necessarily need to. So I propose this 3-step program, which is to ask yourself, if this code is broken or malicious, what can happen? You think about it for a bit. And if you come back and say, not much, you're wrong, go back to step 1. No, I mean seriously, if you take a piece of software that seems like it can do nothing wrong, but its install script has a root shell backdoor in it and run it on your infrastructure, you're completely compromised. Everything has risks. You need to identify what they are and deal with them. And think about what can be done to mitigate those risks. So I wanted to give some concrete examples, and this was really hard for me. Like, for all I said about how hard this is, I don't think that anyone is bad or incompetent for making mistakes in this area. I make mistakes. Daniel Bernstein, who is one of the most brilliant cryptographers of our time, his original ED25519 code had a bug in it that wasn't found until someone tried to formally prove it correct. It would occasionally generate incorrect results. So everyone makes mistakes. And that's fine, but we need to understand the mistakes to learn from them. So I've given an example here. So on the screen, is a incredibly commonly, at least in the past, deployed piece of JavaScript code for secure random number generation. And this has been used on hundreds of websites, including many, many Bitcoin websites, to generate keys for wallets and for signing. It wasn't even created by someone in the Bitcoin ecosystem, but it was widely picked up by it. Now, it has a couple of things that are sort of funny about it that a reviewer would pick up, at least one with domain expertise. So one is that there's a check in it where it checks to see if window crypto, which is the cryptographically secure random number generator, is available. And if it's not available, it just doesn't use it. It doesn't throw an error, it doesn't do anything, it just doesn't use it. Now, what it does use is it uses math.random. And in most browsers, math.random is a 48-bit linear congruent generator. So there's only 2 to the 48 possible states for it. And it's also, in most browsers, seeded from the time at browser start. So this value is pretty predictable. And then it also uses the time when it was run. But that's also pretty predictable. And so if you're in this state where you've not used the secure random number generator, you're using something that maybe has in the order of 50 bits of entropy at most, and probably quite a bit less. Now, with the power of a billion imbeciles, an attacker can search that space. It's actually quite practical to do so. And they could discover private keys as a result of doing so. Now, fortunately, window.crypto is available in all current browsers. And so the state where you don't have it shouldn't be happening very often. So that's good at least. But I had complained about this code to people using it because it just looked unsafe. Now, what I didn't see, and what I've tried like 12 people now, what virtually no one I've shown this to, even telling them that there was another issue here, saw in this, is that, well, there was another issue. And that is that there's this comparison with Navigator at version, the value 5. Well, Navigator at version is a string. And if Navigator at that test returns false, then it doesn't use the secure random number generator. Well, it's always false. This code never uses the secure random number generator, not once. And so you could also end up in this state if you use the code in web workers, which was the source of a related bug on some Bitcoin websites in the past. But you don't even have to have that problem. It never did it. So that's what happens when you don't select things correctly. So another concrete example is that a very popular Bitcoin wallet deployed a message encryption function using ECIES. So ECIES is it's not correct to say it's standardized, but it's a well-studied way of doing message encryption with elliptic curve cryptography. And I say it's not standardized because there's not like test vectors and things like that. You could implement it on your own, and your implementation won't match anyone else's. But it's well understood, and if implemented correctly, it's secure. So they implemented this using code found on GitHub. And the code found on GitHub was widely linked all over the internet. It was talked about on Bitcoin Talk. People who know cryptography were talking to the author about it. The author gives me an impression of somebody who was sort of new to programming, right? Like he was really excited about it. So this wallet picked it up, and they reviewed it. Good for them. And they found in it that it used an insecure random number generator. It used like the Python percent twister stuff. And so they fixed that. But what was actually implemented there wasn't ECIES at all. It was some other cockamamie thing that the author just sort of magicked. And it had a bunch of other problems. So a couple of the problems that it had was that if someone was running a decryption oracle, like a site that would decrypt things and throw error messages back at you that let you know what was in the ciphertext, you could send it 2 to the 16 messages, collect the results, and then take another message to that same destination that you wouldn't have decrypted. You can use those 2 to the 16 results and decrypt the message. So it's a decryption oracle like that. This scheme directly leaked 7 bits of the plaintext in every 256 bits that it was encrypting. It also had this issue where if you sent some messages through it, it would just silently corrupt them on decryption, including the all 1s-bit message. So you send like hex FF through it, the result would come out as line noise. And it was just a silent corruption. So all of these issues in it I found in about 10 minutes. Because I have domain expertise in the kind of crypto system stuff this is using. And there are probably more problems with it. I stopped looking at that point. Now, the authors of this wallet software removed the software, took it down, took that feature out in about 1 more minute after my report. So, and I don't think that they did wrong so much here, right? I think that they're very competent and they responded in a very responsible way. Other people I've worked with have not been so responsible in the past. And other wallet vendors who have done similar things. So the same author of this freaky code had written a bit of signing code that another wallet vendor included in their wallet. And that signing code had the same kind of insecure RNG, and that wallet vendor didn't even fix that. They deployed it with the insecure RNG, and it resulted in a CV against the wallet. In theory, if you use sign message in that particular wallet, your keys might be exposed by it. But finding these problems requires a lot of domain expertise. Like, okay, go ask someone who knows about these things. Doesn't scale particularly well. So what can we do to do better here? So I've proposed a number of sort of risk mitigation techniques that I think would help if people were doing these things, or more of them more often, it might help advance the art here. One is to ask, is this software intended for your purposes? If this is someone's I'm learning to code project, great. But maybe you don't want to secure $1 million in Bitcoin with it. Right. Are the authors taking the cryptographic consideration seriously? And you can look at this in their discussion. How do they respond to security concerns and issues? You can look for a review process. Is there one? So one of the other adages in the crypto space is that anyone can create a crypto system which they themselves cannot compromise. And it's very true. And that's why one of the best ways to learn about cryptography is to break crypto systems. So any kind of cryptographic software should have review, some level of review. And if there is review, the review can be made available to its users, and you should be able to look at it to get a feel of how things are being handled. Sometimes people say, well, this is used everywhere. Obviously, it's been reviewed. But nothing can be more true than this. People adopt things because they're adopted, and things have gone out and been used, which I think no one actually ever looked at the code in. So you can't go by wide use to tell if something has been reviewed. Although, all things equal, wide use is good too. And a touchy one, I think, is also, what is the experience of the authors, right? If someone's a domain expert, there's power in that. And I don't mean to imply that only an elite group of people can write cryptographic software, because it doesn't work. I mean, if we're going to be frank, all the software that touches, say, the Bitcoin space is to some degree or another cryptographic software. And so, I have to write all of it? It's ridiculous. So, but you can look for things like, do the authors of the software have a deep understanding of what they're doing? Because without a deep understanding, even if you understand the procedure, if you don't understand the reasoning for why you do things in a crypto system, then you won't spot all of the subtle assumptions that you have to satisfy. But it's hard, because if you're not yourself an expert, it's easy to mistake this punditry for expertise. And someone can sling a bunch of technical terms at you, and, well, it all sounds equal because you don't know about that area. I think that one of the things you can do, though, is to look for the author sort of trying to extend their reach. That they're learning, they're citing sources, that they're sort of expanding their knowledge. And there's a process around sort of excellence in knowledge, trying to evaluate their technical skill. One thing to look for is the software documented? When we write complicated pieces of software, they are unsafe to maintain if their internal assumptions are not documented. So you should look for internally to software is there documentation explaining what's going on, because you can have the smartest person in the world, but he won't remember what he was thinking a year ago when he goes to change it. And are its assumptions about the outside world clearly documented? I mean, how can you know that your use of it isn't violating its assumptions unless it's told you what its assumptions are? I think you can look for software portability, because people who are working hard to produce good software will tend to make their software more portable. And also, when you try your software in lots of different environments on lots of different applications and machines, you'll expose bugs that you wouldn't have seen otherwise. One of the reasons that we can build really complicated things in the form of software is because it's possible to build automated tests for software in a way that you cannot do for a mechanical device. And so software should be using this power of testing to explore the space of it. Unfortunately, it's possible to make tests that just tell if the software runs, and it's kind of meaningless. So a technique that I suggest is, if there are tests, you go to the software and add bugs. And you don't have to understand the software to add some bugs. And see if the tests fail. It's something that anyone can do. And that'll give you a feel. And you might find that the software doesn't do so well. But then you can iterate with the authors to improve it. You can compare it against your other risks, and you can make a decision whether to use it. You can also look in general for the adoption of best practices. Now, if you're not working on this kind of software, you may not know what the best practices are. There's a lot of disagreement about what best practices look like in software. One of the most competent programmers I know in the C language has this rule where he writes software with basically no unnecessary white space and no unnecessary parentheses. And everyone else hates it. Now, having worked with him for some time, I actually like it a lot. When you get used to it, you start to see things in it that you wouldn't normally see. But there's a lot of debate around this, and I'm not trying to propose a specific standard for how you write software. But if people are doing a good job, they will have standards, and whatever they are, their enforcement leaves evidence. So in review, you will see people saying things about adopting best practices. And you can also ask. You can ask an author of any cryptographic tool, what have you done to mitigate risk? And anyone who is an author of a cryptographic tool should have an answer to that. And if they don't have an answer or a list of answers, then they probably haven't given it much thought. So a lot of this really reduces to looking for conscientious software development, and that is not enough to guarantee secure cryptography. But without it, I don't think we can have secure cryptography. So it's necessary, but not sufficient. I found often in the wider ecosystem that people's enthusiasm about software is often inversely related to how rigorous its development was. And there's a good reason for this, right? If you spend a lot of time making the software secure, it'll have no features. There needs to be some balance and compromise here. One thing that's to keep in mind is that for cryptographic concerns, iteration doesn't work so well. Move fast, break things is a good mantra, and it's very useful. But if you've lost your privacy or your bitcoins, you're not getting it back. And so that the fact the next version fixes the problem, it doesn't help. One issue to watch out for is sort of crypto laundering. People will take this, like, I'm learning to code program and put it in a nice, shiny, professional app. I don't think that you should refuse to trust people that when you take their software that they haven't done the work, but you should refuse to trust them. You can trust but verify. And when you verify that good practices are being used in the parts that you're taking, you create a market pressure to do better. And you give reason for people to feel like their time invested in making more secure systems is well worth it. Finally, this is, I think, a somewhat tricky point. Some of the things that we justifiably want to do violate good practices. Now, I just said before that there's no sort of authority on what a good practice is. But name a good practice, and there's someone who wants to do something that inherently violates it. So people are very opinionated about this stuff. So I'm going to give some opinions, and I know people will disagree with them. So I think that for general cryptographic code, it is unsafe to write general cryptographic code that does not deliver constant time operation. I also think that it's unsafe to write general cryptographic code that can't clean up and avoid memory leaks of private information when it runs. I also think it's very inadvisable to write cryptographic code in languages which aren't type safe, where the language won't automatically catch comparisons with the number 5 in the string and things like that. So all of these points that I just made basically said never write crypto code in JavaScript ever. And that is a ridiculous proposition, right? Because it is the best deployment platform for software in the world available today. And so I don't really know how to weight that. But to say that when you set some requirements on your applications, you are guaranteeing that you are excluding some secure practices sometimes. And you are excluding the contributions of some people who have some good thoughts on this stuff. Because I won't write JavaScript crypto code, right? And I'm not alone. But that doesn't mean you don't do it. But you should be keeping that in your mind and weighing that against the other factors. And so maybe you want to see more rigorous testing in something like that. Or you want to architect your application around making sure those things that you can't achieve are not an issue. It's just something to keep in mind. So after all I said, I still think I know nothing about the subject. This is really a vague art right now. And I think that we need to learn more about it and demand more about the cryptographic tools that we are using, and so that we can advance the art. And in the Bitcoin space in particular, I worry that if we don't advance the art, there will be more big events, more millions or billions of value lost. And the answer is to start like regulating people and saying Bob can't write cryptographic code is something that will come out and we'll have to fight against. And that would be directly opposed to the kind of decentralization that I think that makes Bitcoin interesting. But to have the freedom to build these systems into the explorative space of what's possible, we have to sort of control ourselves. We have to be responsible. And we have to work towards that because we don't know how to get there today. So I'm very interested in techniques and tools that people have found to make good selection of cryptographic stuff, and also things about building cryptographic stuff, because I do that too, although that's its own talk. So I've reached the end, and I'm right on time. So thank you, and I'd be glad to answer any questions.
So you made a comparison to civil engineering, and civil engineering has a liability.
It does.
To people who are developing, plans for buildings and things like that, to incentivize safe building or disincentivize bugs.
Yeah.
So do you think that software engineers should also begin putting skin in the game and actually assuming some liability for their bugs?
So it's not just civil liability, right? In some places, in Israel, for example, you can go to jail. You can be criminally prosecuted for incompetent civil engineering. This is a tricky subject because the greater the responsibilities, the greater the barrier to entry. And one of the fantastic things about software is there's basically no barrier to entry. If you have a computer, you have all the tools you need to be a world-class programmer just by downloading them. And so it's more costly to put restrictions on software than it is to put it on other fields. Like, few people are amateur civil engineers. I don't know how society is going to weigh this going forward in the future. As a software engineer myself, I can say that if there were extensive bonding or licensing requirements, I would potentially not be in this space. But we do have to weigh that. I think that maybe we can sidestep this by upping our art and doing better so that we don't need the backstopping of regulatory requirements. And I also think that it's not clear that liability doesn't exist, and maybe we just haven't seen what that looks like. And as software becomes more integral to more important things, we're going to see more litigation related to incompetent software. And as courts become more versed in what good software looks like, we may start finding negligence in cases where software doesn't doing what it should do. But that's something we'll find out in the future.
So as a real quick follow-up, like alternatively then, do you think that something like certification or insurance against bugs for like professional companies that are developing code, not that's free and open source, but stuff that people are actually paying for, do you think that could help?
I think we're unlikely to see much in the way of insurance without liability.
Right.
Because that's the requirement for it.
But it's contractual liability, right? And legal liability.
And this actually exists, right? Contractual liability for software correct behavior already exists in the wider world, and people should make more use of it. So I think that it's useful things to do there, sure.
Cool.
Go ahead.
So of the new things you presented here, one of them was have multiple ways of unlocking the transaction by presenting a Markle root, right? And then there was another step after that to avoid how many leaves you had, and I did not follow what you said there.
Yeah, sorry about that. I had more slides, but I cut them down. I can show you the point in the Bitcoin Wizards log where this got discussed too. The general idea is that instead of you constructing, you fully materializing this tree of n of n keys that could possibly be permitted.
Yeah.
You present the hub keys that get contributed to it, it gets summed up to the network when you're presenting your signature, and you ask the network to do the summation for the specific n of n that you want out of this collection of m inputs. So I can make a script hub key that just has a list of public points, and then I can have a TREECHECKSIG operator that knows how to sum up the public points or some subset of them, and I can signal what subsets are permissible to accept the signature. Okay, well we can talk about a bunch of stuff, like we have the docs to throw at me. Okay.
But you didn't mention code coverage as a technique for testing.
No, well, so I was.
You mentioned adding bugs on purpose.
Yeah, so I mentioned, so I originally wrote code coverage, but then I realized that actually if you tell people to add bugs on purpose, that actually doesn't, you can't pass that test unless you basically have 100% code coverage. Yeah. So I thought it was kind of redundant to list code coverage. If I were doing a talk on techniques that I think are good to use to build secure cryptographic software, I have like a list of 40. And that's one of them, is to make sure you have 100% branch coverage. Or the name is very covered.
Yeah, the specific disastrous example you put a bit copy.
Yeah, you're never actually running that part. Yeah, actually, that's one of the reasons that code coverage is super useful. is because it sort of double checks your assumptions. Like, oh, this code's never running. That's strange. Yeah. Also doing the bit where you add bugs. If you added a bug into that section that never runs, well, the test couldn't have failed.
Assert false is the simplest way then.
Yeah, that's true.
No more questions? I mean, are we?
You don't have to ask about material on the slides. Like, you can ask me about other stuff too.
Brian?
Do you think it's possible to implement the consensus rules and
We have a question right here.
Yeah, he's asking a question. I'll repeat it.
Do you think it's possible to implement the consensus rules of Bitcoin in another language besides C++ and know that it's accurate?
So do I think that it's possible to implement the consensus rules of Bitcoin in another language besides C++ and know that it's correct? So in decentralized consensus, we have this problem that correctness is actually the less important criteria. Consistency is more important, because correct or not, if nodes are inconsistent, the state will split, and this is disastrous. So can you sort of re-implement Bitcoin Core or re-implement the Bitcoin protocol in other languages and have a hope of success? And this is tricky, because I don't want to answer no, but I don't know how to answer yes. So there's a bunch of research actually into proving that different pieces of code compute the same output. And it turns out that anything more complicated than a context-free grammar, the problem of comparing two different programs and deciding if they're the same is undecidable. So in the worst case, you cannot decide if whether two Turing-complete programs compute the same thing with a program. That's kind of academic. In practice, I think you can get pretty close, and it really depends on what the failure modes are if you do fall out of consensus. So if you fall out of consensus and the result is a denial of service attack on a service you run, yeah, no problem. You can get close enough that that's reasonably unlikely, and maybe you only fall out of consensus every once in a while. I think the most important thing to do is to understand the contours of the problem and how hard it is, and to work hard at it and approximate it. Now, keep in mind that Bitcoin Core is not necessarily consistent with itself. And there have been bugs in the software. For example, Bitcoin Core used to use BDB for the blockchain database. In BDB, two copies of the same software on the same hardware, the same OS, would not necessarily be consistent with each other, because there was some non-determinism in BDB that changed its behavior based on the order that blocks are written to disk. And under certain circumstances during large reorganizations, some nodes would allow the reorganization to occur, and other nodes would run out of locks because of how the data laid out onto disk onto them. And then Bitcoin Core would break from the same version on the same OS with the same software. I think that back earlier in Bitcoin's history, we didn't understand quite the importance of consistency. And so when we're picking tools that go into Bitcoin Core, we're performing a cryptographic operation, the consensus of the network, and we have to understand our assumptions. And one of our assumptions is that all the computers will behave consistently. And so when we have a dependency, we have to ask, will that dependency obey that assumption? And it turns out that most software is not written for consensus systems. And most software that you go and find isn't consistent. And one problem is that the authors of the software will go fix bugs, which is great, fix bugs. But then it makes it inconsistent, so we have to control that. That's one of the reasons that today in Bitcoin Core, we internally embed the database that we use for storing the blockchain. So I hope I didn't dance around that too much. I'm just trying to say that it's hard.
Does Bitcoin involve any floating point operations as part of its normal?
Not as part of the consensus.
Okay, so even like when it resets work difficulty, that's all?
Yeah, that's all done with large 256-bit integers for the work resetting. So the question was, does Bitcoin involve any floating point? And no, because normally, so floating point, IEEE floating point is well specified, but what compilers normally implement is not IEEE floating point. It differs from architecture to architecture. I've actually seen cryptocurrencies that have gone and put floating point in their consensus code, and it's totally breakable. It's quite frightening. So don't do that. Don't put floating point in consensus code. So here, I'll give a safe example. So let me make a little philosophical point here. When I make a negative comment about some other cryptocurrency, it gains me nothing. So do not expect people who are big names in this space to go around telling you about what's safe in other systems. In particular, not only does it not gain me something, in some cases I have been threatened because of negative things I've said about someone's pump and dump scheme. And so I tend to be pretty conservative about it. In this case, though, an example I would give you is SolidCoin, which implemented a proof of a difficulty change over time that involved transcendental functions in floating point. Go ahead.
You mentioned at the beginning that you're one of the 5 core contributors and that you spend a lot of your time not necessarily writing code, but reviewing.
Yep.
So I was curious if you could talk a little bit more about, like, beyond the 5 of you, how many people are contributing work to Bitcoin on a regular basis?
Yes. So beyond the 5 sort of core committers to Bitcoin Core, how many other people are working on it? So if you go by the sort of Git commit logs, you'll see that there's about, in the last release, for example, in 0.10, there were about 100 people that contributed in some way. Now, some of those contributions were they fixed a string, a spelling mistake or whatever, and some of them were more substantial. So there's kind of a power law distribution. I would say that there's on the order of maybe 10 to sort of 12 people who are contributing kind of at the same level that all of the core contributors are. And then there's sort of people that fix little bugs, and it falls off after that. It's a hard area to contribute to, and it's actually quite frustrating and unrewarding to join into the project. And we're trying to improve it. Because part of the problem is you show up with something neat, and now you have to pass me for review. And I think everything is broken. So I try to not be a barrier like that, but it's really hard. So we've been doing a bunch of work to make the software more modular. It should make it more easy for people to contribute in safe ways and expand the contributor base further.
Can we get last 2 questions? Because we have to head out soon.
All right. What do you think of the provably accurate new Stellar?
Well, remember my comment before. I've made some public comments on this, so I will repeat them. I have a general complaint about the consensus model used in Ripple, Stellar and New Stellar, that I complained about when Ripple was first announced. That basically there's a strong assumption in the system, and this is true for all of them. Amusingly, the Ripple model didn't achieve its properties even when the strong assumption was met. The new system is provable, meaning that it should meet its properties even when the strong assumption is met. Back when Ripple was released, the strong assumption wasn't even well described. So there's a bunch of participants in the system, and they have trust that they put out into the network. And I went and posted about this and said, well, wait a minute. There are certain trust topologies, ways that people trust other people, that are guaranteed to fail. How do we know that the network won't develop those topologies, and what is the actual criteria? I can show you a failing one. So that's the strong assumption, that people will configure their trust in a certain way. Now, the new Stellar paper goes and formalizes that assumption a bit more. And so we can say that there is this intersection requirement. The trust has to overlap in certain ways in order for the system to achieve consensus. But they haven't formalized the process for achieving that outcome. Now, before you think I'm throwing a lot of stones here, I should point out the Bitcoin security model also has this kind of strong assumption. So you can say that in Bitcoin, our strong assumption is that a majority of the hash power is honest. And you can say that so long as it's honest and the honest participants aren't partitioned from each other in the network, the system will achieve consensus reliably, eventually. But why is half of the hash power honest? So you can fall back to a set of weaker assumptions that we wave our hands a little bit more about and say that there's economic incentives to behave honestly and so on. And we've done that in the Bitcoin ecosystem. We've stated a strong assumption, talked about its limitations, talked about why we think those limitations are plausible. And that space has been explored, and it's still being explored by researchers and developers in software. So I'd like to see more of that in the sort of Ripple Stellar world, sort of really being frank about the assumptions and trying to figure out how plausible they are. One way to meet the assumption in the system, this trust intersection assumption, is to be completely centralized. If everyone trusts the same party, then your trust completely overlaps, or the same set of parties. And that's a system that's secure but not decentralized. And I actually think there's a lot of place in the world for systems that are less decentralized but get better properties, better scaling, and so on. So I hope that answers the question.
Last question, make it good.
So when you describe the problem that happened with VirtualDB in the earlier version of it kind of shows that using the code as a baseline for consensus is problematic sometimes. Would there not be a value of like documenting precisely the consensus in a separate document?
Yeah. So there's the question is the Berkeley DB stuff showed that there's a problem with the code as the spec. And wouldn't there be value in having another documentation for the consensus? And there are many values, but maybe not the ones you're thinking about. So there is documentation about the behavior that we expect from the system. It's not necessarily great. There's the developer docs and then the protocol specifications on Bitcoin Wiki. I wouldn't suggest trying to implement from that. I think at the moment it's all relatively complete. Maybe you'd have a fighting chance of implementing from it and getting something consensus consistent. Maybe not, I'm not sure. That could be improved and should be improved because that helps people's understanding, and so we can make changes to the system more safely. But in terms of the practical effect, if the system, whatever code is actually running, fails to come to consensus or comes to consensus in a particular way, we're kind of stuck with it, right? If the spec says one thing and the code does something else, we're going to need to change the spec because like the money has already moved. And we go, you know, too bad, let's allow everyone to double spend. That's not reasonable. So work needs to be done there, but it doesn't replace actually achieving consensus in practice in the network.